The nearest star system beyond our Sun is more than 24 trillion miles away. By the end of this video, you will understand the 30 essential breakthroughs that must happen before any human crew can make that journey. Some of these breakthroughs are already being tested in labs today, while others may not be possible for centuries. What will it take for a species born on one planet to reach another star? The answer begins with the fuel itself. Chemical rockets are magnificent at punching through Earth's atmosphere, but they are tragically inefficient for crossing the vast emptiness between stars. A spacecraft using today's most powerful chemical engines would need tens of thousands of years to reach even the closest star system. That is not a journey. That is a fossil. For humans to reach another star within a single lifetime, we need a propulsion system that burns fuel in a fundamentally different way. This is where fusion propulsion enters the picture. The idea is simple in concept. Instead of breaking chemical bonds between atoms, you fuse atomic nuclei together, releasing millions of times more energy per kilogram of fuel. Controlled nuclear fusion, the same process that powers the Sun, offers a specific impulse, a measure of how efficiently a rocket uses propellant, that is hundreds of times higher than the best chemical engines. The challenge is not just making fusion happen in space, but doing so inside a reactor that is light enough to launch from Earth and reliable enough to run for years without failure. Researchers have proposed designs like the fusion-driven rocket, which uses small pellets of fusion fuel that are compressed and ignited by powerful magnetic fields or lasers. Inertial confinement fusion, where a tiny capsule of fuel is crushed by intense energy beams, is another approach being tested in laboratories on Earth. The goal is to create a series of controlled micro-explosions that produce thrust directly, without the need for heavy turbines or massive radiators. But sustaining a fusion reaction in the vacuum of space introduces its own set of problems. The reactor must survive extreme temperatures, radiation, and magnetic forces. It must also provide electrical power for the entire ship, so the fusion system serves double duty as both engine and power plant. That dual role makes the engineering even more demanding. Even if we master fusion propulsion, the travel time may still stretch beyond what is comfortable for a human crew. A fusion rocket could cut the journey to a nearby star down to perhaps 50 years, maybe less with advanced designs. That is a tremendous improvement, but it still means entire generations of crew members would live and die aboard the ship. For a voyage that fits within one person's lifetime, we may need something even more exotic. That points toward technologies that push physics to its limits, where the energy source is no longer matter but something far stranger. Antimatter offers the most concentrated energy source in the known universe. When a particle of matter meets its antimatter counterpart, they annihilate each other in a flash of pure energy. This conversion is 100% efficient, meaning every bit of mass turns into energy. Compare that to nuclear fusion, which converts less than 1% of its fuel into usable energy, and chemical rockets, which release barely a billionth of the mass they carry. The difference is staggering. A single gram of antimatter, if perfectly annihilated, releases the same energy as 40 kilotons of high explosive. For a spacecraft headed to another star, that kind of density means you could carry a tiny amount of fuel and still have enough energy to accelerate for months or even years. The basic design of an antimatter engine sounds almost too simple. You inject a stream of antimatter particles, usually antiprotons, into a reaction chamber filled with ordinary hydrogen. The instant they meet, they annihilate, producing a spray of high-energy particles called pions and muons. These particles shoot out in every direction, but you do not want them going sideways or forward. So you place a powerful magnetic field at the back of the chamber, called a magnetic nozzle that channels the charged particles into a narrow exhaust beam. That beam pushes the spacecraft forward, just like the hot gas from a chemical rocket, but with far greater speed and efficiency. No heavy combustion chambers or turbopumps are needed. The magnetic field does all the work of directing thrust, but the promise of antimatter propulsion comes with a price that is almost unimaginably high. The first problem is production. Today, we can create antimatter in particle accelerators, but only in vanishingly small amounts. The Large Hadron Collider, for example, produces about 10 nanograms of antimatter each year. That is barely enough to power a single light bulb for a few hours. To fuel a starship, you would need grams, thousands of times more than the entire world's current annual output. Scaling up production would require dedicated antimatter factories, enormous rings of magnets and accelerators that run on vast amounts of electricity. Even if we built such a facility, the cost would be astronomical. Some estimates put the price of 1 gram of antimatter at more than $100 trillion. Then comes the problem of storage. Antimatter cannot touch ordinary matter or it annihilates instantly, so you have to keep it suspended in a perfect vacuum, held in place by electric and magnetic fields. Devices called penning traps use a combination of a strong magnetic field and an electric field to confine charged particles like antiprotons. These traps work well in the laboratory for tiny amounts, but storing grams of antimatter is a different challenge entirely. The magnetic fields would need to be incredibly strong, and the trap would have to be perfectly sealed for years or decades. Any tiny failure, a power outage, a leak in the vacuum, a stray piece of debris, and the antimatter would contact the walls of the container. The result would be an explosion far more powerful than any chemical bomb, potentially destroying the spacecraft and everything inside it. Despite these enormous hurdles, antimatter engines remain one of the most studied concepts for interstellar travel. They offer the highest theoretical specific impulse of any known propulsion method, meaning the spacecraft could reach speeds approaching a significant fraction of the speed of light. A ship powered by antimatter could theoretically make the trip to the nearest star in under 50 years, perhaps even less with advanced designs. For a human crew, that timeline begins to feel manageable within a single lifetime. But even antimatter may not be the final answer. The difficulties of production and storage are so extreme that some researchers view antimatter as a stepping stone to something even more speculative. If we ever learn to harness the vacuum of space itself, or to manipulate space-time in ways that bypass the need for propellant, then antimatter might become just a historical footnote. For now, it stands as the best-known path to reaching another star, a path that demands breakthroughs in particle physics, materials science, and energy generation that we can barely begin to imagine. The technology of antimatter propulsion is so demanding that it forces us to ask a different question. What if we removed the fuel entirely? For a starship, fuel is mass, and mass is the enemy of speed. Every kilogram of propellant you carry must itself be accelerated, which requires even more propellant. It is a vicious cycle that makes every extra gram cost an enormous amount of energy. But what if the energy that pushes the ship does not come from anything on board? What if it comes from a source far away, a source that never runs out as the journey progresses? That idea leads to one of the most elegant concepts in interstellar travel, the solar sail, or more accurately, the light sail. Imagine a vast, ultra-thin sheet of reflective material spread out like a mirror in space. Instead of burning fuel, it catches the gentle push of photons, particles of light. Every photon that bounces off the sail transfers a tiny amount of momentum. Alone, that push is imperceptible, but over days and weeks with a powerful enough light source, the sail can accelerate to speeds that would dwarf any chemical rocket. The trick is that the light does not have to come from the sun alone. If you build an enormous array of lasers, either on the ground or in orbit, you can focus a beam of coherent light onto the sail, giving it a constant, sustained push. This is not science fiction. A project called Breakthrough Starshot is already exploring exactly this concept, with the goal of sending a tiny, gram-scale probe to the Alpha Centauri system within a generation. For this to work, the sail must be almost impossibly thin. We are talking about sheets of material perhaps a few hundred atoms thick, with a mass so low that it barely registers. The material must also be nearly perfectly reflective. Even a tiny fraction of absorbed light would heat the sail to destruction. Researchers have proposed using layered structures of silicon dioxide and molybdenum, essentially a mirror engineered at the atomic scale. The sail would need to withstand the intense laser beam without tearing or warping, all while staying perfectly flat so the light pressure remains even. Any slight misalignment could cause the probe to tumble off course, but acceleration is only half the problem. When the probe arrives at the target star system, it will be moving at a significant fraction of the speed of light. Slowing down is an entirely separate challenge. Without a braking system, it will simply zip past Alpha Centauri in a matter of hours, sending back only a blur of data. To decelerate, the sail would need to reverse the process, using the light from the destination star to slow down. That requires an enormous sail that can also serve as a drag surface, or a separate laser array built at the other end. For now, the initial Starshot plan calls for a flyby mission that simply captures images and measurements during the brief passage. Slowing down remains one of the greatest unsolved problems for any interstellar sail mission. Even with these hurdles, the light sail approach holds a profound advantage. It removes the need to carry propellant entirely. The energy source stays behind on Earth or in orbit around the Sun. That means the spacecraft itself can be incredibly light, which in turn allows for higher speeds. The ultimate limit is the power of the laser array. And that brings us to the next essential breakthrough, a power source that can feed an interstellar laser system for years without interruption. Without that kind of energy, even the most perfect sail will never catch the wind it needs. That laser array would demand more electricity than the entire world produces today. To push a light sail to a significant fraction of the speed of light, you need a beam with a power output measured in gigawatts, meaning billions of watts continuously for years. No single power plant on Earth can deliver that kind of energy to a single point in the sky. The only viable solution is to build the power source where the sunlight never fades, in orbit. Gigawatt-scale space-based power is therefore one of the most critical breakthroughs on the path to another star. The idea is to construct vast arrays of solar panels in space, far above the interference of Earth's atmosphere and the cycle of night and day. In orbit, the sun shines 24 hours a day, and the intensity of sunlight is roughly 7 times higher than at the surface of the planet. A single square kilometer of advanced solar cells could generate about 1.5 gigawatts of electricity. That is enough to power a small city, but for an interstellar laser, you would need many such arrays, carefully positioned and aligned, capable of feeding that energy directly into a network of phased laser emitters. Building something that large in space requires a fundamental shift in how we manufacture and assemble orbital infrastructure. Today, every satellite and space station component is built on Earth, packed into a rocket, and launched at enormous cost. The largest solar arrays ever deployed in orbit, those on the International Space Station, produce only about 1/4 of a megawatt combined. That is 3,000 times less than a single gigawatt. To reach the power levels needed for interstellar propulsion, we would need to either launch tens of thousands of such arrays, which is economically impossible, or learn to manufacture solar panels directly in space using materials gathered from the moon or asteroids. That is a whole separate breakthrough in itself. involving robotic factories that can extract silicon, assemble cells, and unfurl kilometer-wide structures without any human hands. Even if we solve the construction problem, there is the challenge of heat. Every electrical system generates waste heat, and in the vacuum of space, there is no air to carry it away. The only way to dissipate heat is through thermal radiation, which is much slower. A gigawatt-scale power plant would produce staggering amounts of waste heat, enough to melt ordinary electronics. The radiators needed to shed that heat would have to be enormous, perhaps even larger than the solar arrays themselves, and made from materials that can operate at high temperatures without degrading. Engineers have proposed using liquid metal coolants like liquid lithium or liquid sodium to carry heat from the power generation systems to massive radiator panels. Those panels would glow red-hot in the infrared, visible as a faint glow from Earth, as they radiate the excess energy into the blackness of space. Keeping the whole system stable and functional for decades is an engineering problem that rivals the propulsion challenge itself. Then comes the economics. Building a gigawatt-scale power station in orbit would cost trillions of dollars by current estimates. No single nation or company can bear that cost. It would require a global collaboration, perhaps over many generations, similar to the way we built the International Space Station, but on a scale 1,000,000 times larger. The payoff, however, is not just interstellar travel. Such a power infrastructure could also provide clean, unlimited energy to Earth itself, beaming it down via microwaves to ground-based receivers. That would fundamentally change the world's energy landscape, solving climate challenges and providing power to remote regions. In that sense, the investment in space-based power serves a dual purpose, making it more than a one-way ticket to the stars. But even with a massive power station in orbit, the spacecraft cannot always draw energy from a fixed laser array. Once it leaves the inner solar system, the beam becomes too weak and too diffuse to push the sail effectively. For the long cruise phase, and especially for maneuvering near the destination star, the ship must carry its own energy source. That is why the next breakthrough is just as essential. Efficient energy storage systems that can hold enormous amounts of power for years without degrading. Without that, the ship would be a ghost, drifting silently through the void with no way to adjust course or slow down. That need for storage forces a fundamental rethinking of battery technology. Even a ship equipped with the most efficient fusion engine or the most powerful laser sail cannot draw power continuously during every moment of the journey. There will be long coasting phases when the propulsion system is idle, times when the spacecraft must make precise course corrections, and emergencies when backup power becomes the difference between survival and drifting forever in the dark. The energy storage system must hold enough electricity to run every life support system, every computer, every navigation tool, and every scientific instrument for decades without a single recharge from an external source. That means the storage density, the amount of energy packed into each kilogram of battery, must be orders of magnitude higher than anything we have on Earth today. Current lithium-ion batteries, the kind that power your phone and electric car, store about 250 watt-hours per kilogram. That is enough to light a 100-watt bulb for 2.5 hours from a kilogram of battery. To power a city-sized starship with its thousands of inhabitants and their complex needs, you would need millions of kilograms of such batteries. That mass would crush the ship's performance before it even left the solar system. The only way forward is to push energy density to its absolute physical limits. Advanced lithium-ion chemistries using solid-state electrolytes or lithium-sulfur compounds could double or triple that figure, perhaps reaching 1,000 watt-hours per kilogram. Supercapacitors, which store energy in electric fields rather than chemical reactions, can charge and discharge almost instantly and last for millions of cycles, but their energy density is currently far lower than batteries. They might serve as high power buffers for short bursts, but they cannot replace bulk storage for years of steady use. Then you enter the realm of speculative technologies that seem almost magical. Superconducting magnetic energy storage uses a coil of superconducting wire to store electricity as a circulating current that never decays. The energy density is theoretically very high, and the system can release power almost instantly. But the coil must be kept at cryogenic temperatures near absolute zero, which requires a cooling system that itself consumes power. On a starship, that cooling could be integrated with other cryogenic systems, but it adds complexity. An even more futuristic idea is the nanoscale diamond battery. This concept uses tiny synthetic diamonds that contain radioactive isotopes. As the isotopes decay, they release high-energy electrons that are trapped by the diamond lattice, generating a steady, low-power electrical current for thousands of years. The energy density is enormous, but the power output is very low per battery, so you would need a vast array of them to run a ship. Still, for backup systems that must remain functional for centuries, diamond batteries offer an unmatched combination of longevity and safety. None of these technologies exist today at the scale required. To make them work for an interstellar mission, researchers must discover new materials, new manufacturing methods, and new ways to integrate storage with the ship's power grid. The energy storage breakthrough is not just about a single battery. It is about an entire system of storage, distribution, and redundancy that can be trusted for decades without maintenance. Every watt stored is a watt that might save a life, correct a trajectory, or keep the lights on when the main reactor goes silent. And once we solve that problem, the next set of challenges shifts from the ship's bones to its beating heart, the human beings who will live inside it. Those crews will need air, water, food, and protection from radiation, all of which must be generated or recycled in a closed loop for generations. That is where the breakthroughs in life support and biosphere engineering begin. The human body was not designed for a century-long crossing between stars. Even with the most efficient propulsion and the most compact life support systems, a ship carrying a full awake crew would need staggering amounts of food, water, and oxygen. Every crew member consumes resources every day for decades. Multiply that by dozens or hundreds of people, and the required supplies become a second moon of mass. That is why one of the most critical breakthroughs is a way to pause the passengers themselves, to slow down their biological clocks so that very little time passes inside their bodies while the ship travels through the dark. This is the promise of reliable cryogenic suspension, a state that mimics hibernation but goes far deeper. The idea is not to freeze people solid, because ice crystals destroy cells beyond repair. Instead, the approach is to induce a form of suspended animation by suppressing metabolism to an extremely low level. On Earth, we already use a related technique in hospitals called therapeutic hypothermia. When a patient suffers cardiac arrest or severe brain injury, doctors sometimes lower the body temperature to around 32 to 34 degrees Celsius, just a few degrees below normal. This slows metabolic activity and reduces the demand for oxygen, giving tissues a chance to recover. Patients can be kept in this chilled state for a few days, sometimes longer, and then rewarmed successfully. But extending that to months or years is a completely different challenge. Researchers are exploring deeper torpor states using drugs that inhibit cellular processes, combined with precise temperature control. Some experiments on animals have achieved weeks of metabolic suppression. A few species, like the Arctic ground squirrel, naturally hibernate for 7 months by dropping their body temperature to near freezing while their brain activity all but stops. If we could unlock the same mechanism in humans, we might be able to pack a crew into sleep pods for the bulk of a journey. The ship would need to maintain a steady cold environment, monitor each person's vital signs, and deliver nutrients or remove waste at a very slow rate. The sleeper would experience almost no aging because their cells would be producing energy at a tiny fraction of normal levels, and the damage from time would accumulate far more slowly. But a technique that works for a few months in a lab may still fail after decades. The greatest unknown is whether the human brain can survive such extended suppression without suffering from subtle degradation in memory, personality, or cognitive function. Even if the body is preserved, the mind must return whole, not hollow. That is why any reliable system must also include the ability to periodically wake individuals for assessment, or better yet, to have a fully awake skeleton crew that rotates through sleep cycles. But that brings us back to the problem of resources. If only a small number of people stay awake at a time, the total consumption of supplies drops dramatically. The awake crew would manage the ship, handle emergencies, and maintain the pods of their sleeping companions. Advanced automation could replace much of that awake human attention. A sufficiently intelligent computer system could monitor all life support, adjust temperatures, and respond to anomalies without ever needing rest. That computer would need to be reliable for decades without human intervention, which is a breakthrough in itself. But if we combine fully automated ship management with cryogenic pods that can safely hold a crew for 50 years or more, the equation changes completely. The ship becomes a vessel of sleep with only a handful of people awake at any given time, perhaps just one person per decade. The journey would feel almost instantaneous to everyone else. They would close their eyes in the solar system and open them at another star with the intervening years erased. That is the dream, and the next few breakthroughs are the steps that will make that dream a reality, starting with the machines that must never tire and never fail. Among those machines, none is more vital than the systems that keep the crew alive. On an interstellar ship, the word waste loses its meaning. Every atom must be recycled indefinitely because resupply from Earth is impossible. The nearest star is decades away, and no cargo vessel can deliver fresh water or breathable air across that distance. The ship must become a closed loop, a self-contained world where nothing is thrown away and every molecule is used again and again. Water will be the first resource reclaimed. The International Space Station already recovers moisture from urine, sweat, and humidity in the air. That reclaimed water is purified and used for drinking, hygiene, and even oxygen generation. But the ISS system achieves only about 90% efficiency. On a starship, a 10% loss is catastrophic. After a few years, the crew would run dry. The breakthrough needed is a system that recovers nearly 100% of every drop, with losses measured in parts per million, not percent. Next comes oxygen. Humans breathe in oxygen and breathe out carbon dioxide. That carbon dioxide must be converted back into oxygen. On the ISS, a chemical reactor called the Saboteur system combines carbon dioxide with hydrogen to produce methane and water. The water is then split into oxygen and hydrogen through electrolysis. The hydrogen gets reused and the oxygen goes to the crew, but the methane is vented into space, a loss of hydrogen atoms. For a decades-long journey, such losses add up. A truly closed loop would need a biological system, perhaps genetically engineered algae or bacteria that consume carbon dioxide and produce oxygen plus usable biomass. Those same organisms could also help recycle solid waste. Human solid waste contains water, salts, and organic compounds that plants or microbes can break down into nutrients. Instead of ejecting it into space, the ship would turn waste into fertilizer for hydroponic gardens. Those gardens would grow food, produce oxygen, and absorb carbon dioxide, creating a miniature ecosystem that mimics Earth's great cycles. The challenge is achieving perfect balance. On Earth, natural cycles have evolved over billions of years. On a starship, every variable must be controlled by sensors and automated systems. Too much carbon dioxide and the crew suffocates. Too little oxygen and they starve for air. Any buildup of trace toxins from plastic off-gassing or cleaning chemicals could slowly poison everyone. The margin for error is zero. That is why the life support system must be designed with multiple redundancies and fail-safes, each subsystem backed up by another. It is the most complex environmental control system ever built, more demanding than any submarine or space station. Once that loop is perfected, the next question becomes how to produce enough food to sustain a crew for decades without resupply. Growing food in deep space is nothing like farming on Earth. On the surface, you have soil, rain, sunlight, and an entire ecosystem of microorganisms that break down organic matter into nutrients plants can absorb. Aboard a starship, none of that exists naturally. Every leaf, every root, every grain must be coaxed into life inside a sealed metal chamber where the environment is completely artificial. The breakthrough needed here is a bioregenerative food system that can produce all the calories, vitamins, and minerals a crew needs for decades, using only the resources already on board. The first challenge is gravity or the lack of it. In zero gravity, water does not flow downward. It forms floating blobs that cling to surfaces. Soil would drift away. Traditional hydroponics, where plant roots sit in a nutrient-rich water solution, becomes a messy puzzle. Solutions include using porous materials like clay pellets that wick water upward through capillary action, or misting the roots with a fine nutrient spray, a technique called aeroponics. Aeroponics is especially promising because it uses far less water and allows oxygen to reach the roots easily. But the system must be completely sealed to prevent droplets from escaping into the ship's cabin where they could damage electronics or be breathed in by the crew. If the ship has rotating sections to simulate gravity, the situation changes. Artificial gravity, even if low, will pull water and nutrients downward, making hydroponic systems far more conventional. However, the radius of rotation needed to avoid disorienting Coriolis forces is large. So many early ships may rely on zero-gravity farming for decades before artificial gravity becomes practical. That means engineers must design robust wicking and misting systems that work flawlessly without ever clogging or leaking. The second critical factor is light. Sunlight is too dim and unpredictable beyond Mars. The ship will rely on energy-efficient LEDs that emit only the wavelengths plants use for photosynthesis. Red and blue light are the most efficient, but green light helps plants detect shading and adjust their growth. Researchers at NASA have spent years testing different ratios of red, blue, and far-red LEDs to maximize yield while minimizing electricity consumption. The goal is to produce as much food as possible per watt of power. That means selecting plant varieties with short growth cycles, high harvest index, and compact size. Leafy greens like lettuce, kale, and spinach grow quickly and are nutrient-dense. Dwarf wheat, soybeans, and potatoes have been grown in prototype systems on Earth. Some proposals even include duckweed, a tiny aquatic plant that doubles its biomass every day and is rich in protein. But a diet of only plants would leave the crew deficient in certain amino acids and vitamin B12. To solve that, the ship might include small-scale cultured meat production, growing muscle tissue from animal cells in a nutrient broth. This technology is still emerging even on Earth. The challenge for space is the energy and equipment to maintain sterile conditions, but the payoff is a reliable source of complete protein without the enormous water and feed costs of raising animals. All these systems must be monitored and controlled by automated sensors that measure pH, electrical conductivity, dissolved oxygen, temperature, and humidity. The data feeds into an artificial intelligence that adjusts the lighting schedule, nutrient concentration, and misting frequency in real time. This is not a garden you can water with a hose. It is a precision biochemical factory. the European Space Agency has run long-duration experiments with the Me-Li-SSA project, which aims to create a closed-loop life support system using bacteria, algae, and higher plants. They have grown tomatoes and algae in controlled chambers, and the lessons learned directly apply to interstellar farming. Similarly, a veggie experiment on the International Space Station has successfully grown lettuce and peppers, but those are small-scale demonstrations. Scaling up to feed 100 people for decades requires a leap in reliability and resilience. Even with perfect automation, one crop failure could mean the difference between life and starvation. That is why the food system must include multiple types of organisms, redundancy in seed banks, and the ability to start new crops from stored spores or cuttings. And it does not end with plants. The crew themselves produce carbon dioxide, and plants need that carbon, but plants also release oxygen, which the crew needs. The two cycles must be balanced precisely, and that balance depends on a hidden army of microorganisms living in the water, air, and soil. These microbes break down wastes, fix nitrogen, and protect roots from disease. Without a robust microbial ecosystem, the entire food system would collapse. That microbial ecosystem itself is the breakthrough that ties directly to the next problem: how to maintain the health of the human body in an environment where every surface is antiseptic and every breath is filtered. The human body evolved under the constant pull of Earth's gravity, and without it, the body begins a slow, relentless decline. Bone density drops by about 1% every month in microgravity, as the skeleton no longer needs to support weight. Muscles atrophy, shrinking and weakening because they are not fighting against gravity. Fluids shift upward into the chest and head, causing puffy faces and putting pressure on the eyes, which can permanently impair vision. For a crew traveling to another star, these effects could become critical before the ship even leaves the solar system. A journey lasting decades without gravity would leave the passengers too frail to stand when they finally arrive, if they survive at all. The solution is as elegant as it is ancient: spin the ship. If a large section of the spacecraft rotates like a wheel, the centrifugal force pushes everything outward, mimicking the sensation of gravity. The outer wall of the rotating section becomes the floor, and the inner hub remains weightless. The strength of that artificial gravity depends on two factors: the radius of the rotation and the speed of the spin. You want to aim for a value close to Earth's gravity, about 9.8 meters per second squared. That can be achieved with a small radius and a high rotation rate, or a large radius and a slow rotation. But the human body is sensitive to rotation. If the spin is too fast, the inner ear registers a constant turning sensation, causing disorientation and nausea. Worse, because the gravity is stronger at the rim and weaker near the center, a person's head and feet will experience different forces, leading to strange pulling sensations. This effect, known as the Coriolis force, makes moving objects appear to curve. A simple gesture like reaching for a cup becomes a confusing twist. Engineers have studied this problem for decades. Experiments on rotating rooms on Earth suggest that most people can adapt to rotation, rates up to about 2 revolutions per minute without major discomfort. Above 4 revolutions per minute, nearly everyone feels sick. That means to produce Earth gravity at a gentle rotation rate of 2 rpm, the radius must be about 220 meters. That is the distance of more than 2 football fields from the central axle to the outer deck. A ship with a wheel that large would be enormous, perhaps the size of a small city. It presents a structural challenge that rivals any other part of the mission. The rotating section must be strong enough to withstand the centrifugal stress. Every kilogram of mass at the rim experiences a force pulling it outward. The connection between the rotating section and the non-rotating hub must be smooth and reliable, using bearings and seals that never leak air and never fail. Docking ports and launch interfaces are a nightmare because a visiting ship cannot simply latch onto a spinning target. The hub, which rotates slowly or not at all, is the natural place for docking, but that means the crew must move through a transition zone where gravity changes from 0 to full as they climb down a spoke. That transition can be disorienting and requires careful design. Arthur C. Clarke's 2001 A Space Odyssey popularized the rotating wheel concept with the Space Station V, but the idea goes back much further. NASA studied rotating spacecraft in the 1960s and even conducted ground experiments with volunteers living in centrifuges. Those studies revealed that artificial gravity is possible, but it comes with trade-offs. No one has ever built a rotating space habitat large enough to test on orbit. The closest we have come is the small centrifuge on the International Space Station for rodent experiments, showing that mice raised in artificial gravity develop normally compared to those in microgravity. For humans, the step from mice to an interstellar ship is enormous, but the principle holds. The next question is how to engineer a rotating section that can survive decades of continuous spin, with all the mechanical wear and vibration that entails. The bearings must be nearly frictionless and self-lubricating. The seals must prevent any air from leaking between the rotating and stationary parts. Power and data must cross that boundary through slip rings, which are contact-based, or through wireless transmission. Any failure in these interfaces could force the crew to stop the rotation, losing gravity for months while repairs are made. During that time, the health deterioration would accelerate rapidly. So the artificial gravity system must be designed with backups and the ability to slowly spin up again once the repair is complete. This is not a luxury, it is a medical necessity. Without it, the crew will not survive the voyage, and even with gravity, there is a second invisible enemy that no amount of spinning can block: the shower of cosmic radiation that fills the space between stars. That radiation poses a threat as severe as bone loss, and protecting the crew from it requires an entirely different set of breakthroughs. The emptiness between stars is not truly empty at all. It is filled with a silent, invisible storm of high-energy particles that move at nearly the speed of light. These particles, known as galactic cosmic rays, come from supernova explosions and other violent events scattered across the galaxy. They are joined by sudden bursts of solar particles from our own sun, which can spike without warning. Outside the protective bubble of Earth's magnetic field, the crew of an interstellar ship will face a constant bombardment that can pass straight through the hull, through their bodies, and through the electronics that keep the ship alive. Over months and years, this radiation can damage DNA, increasing the long-term risk of serious health conditions such as cancer. It can also degrade computer chips, disrupt memory circuits, and slowly eat away at the materials that hold the ship together. The challenge of shielding against this invisible threat is one of the most stubborn obstacles on the path to another star. The simplest approach is passive shielding. You place a thick layer of material between the crew and the radiation. Water is an excellent shield because its hydrogen atoms are very effective at breaking up passing particles. Polyethylene, a common plastic, is also rich in hydrogen and works well. A passive shield made of water or plastic could reduce the radiation dose to acceptable levels for a few years. But the problem is mass. To bring the dose down to what we consider safe on Earth, you would need a shield several meters thick. For a large crew compartment, that translates into tens of thousands of tons of extra mass. That is more than the entire launch weight of a super-heavy rocket. Carrying that much shielding would make the ship impossibly heavy and far too slow. It is a dead end for any mission that hopes to reach another star within a human lifetime. That is why researchers have turned to a much more elegant solution: active shielding. Instead of stopping the particles with mass, you use magnetic or electric fields to bend them away. just as Earth's magnetic field deflects most of the solar wind. The idea is to generate a magnetic bubble around the spacecraft, a mini magnetosphere that pushes charged particles aside before they ever reach the hull. In theory, such a field could be produced by a superconducting electromagnet. Superconducting coils, when cooled to extremely low temperatures, can carry enormous currents without any electrical resistance, generating intense magnetic fields with very little power input. The same technology that powers magnetic resonance imaging in hospitals could be scaled up and placed around the ship. The field would need to be powerful enough to deflect particles moving at close to the speed of light. That requires a magnetic field strength measured in teslas, comparable to what is used in particle accelerators. The energy to run these coils is not trivial, but it is far less than the mass penalty of passive shielding. The biggest engineering hurdles are keeping the superconducting coils at cryogenic temperatures for decades and protecting them from the very radiation they are deflecting. Even small impacts from high-energy particles could heat the superconductor and cause it to lose its superconducting state, a catastrophic failure known as a quench. That would shut down the magnetic shield instantly. Another active approach uses electrostatic fields. By charging the outer shell of the spacecraft to a high voltage, you can repel positively charged particles like protons. This method is simpler and does not require cryogenic cooling, but it is only effective against particles with relatively low energy. The most energetic cosmic rays would punch right through the static electric barrier. A combination of magnetic and electrostatic shielding could cover a broader range of energies, but that adds complexity. There is also the issue of maintenance. In deep space, there is no workshop, no supply depot, no spare parts delivery. Every system must be reliable for decades without any human intervention. The radiation itself can cause gradual damage to wiring, insulation, and semiconductor components, eventually leading to failures that no amount of redundancy can fix. That means the materials used to build the shield, the superconducting tapes, the power converters, the cooling pumps, must be specially engineered to survive the same environment they are meant to protect against. This creates a circular problem. You need radiation-tolerant materials to build a shield, but those materials do not yet exist at the required scale. Developing them is yet another breakthrough in itself. Once that loop is closed, the next step is to integrate the shield with the ship's power and thermal management systems. The magnetic field consumes energy, and the coils generate waste heat that must be radiated away. The entire assembly must be lightweight, durable, and self-correcting. An autonomous control system would constantly adjust the field strength based on real-time measurements of the radiation environment. The vision is a ship that carries its own invisible force field, a bubble of safety that moves with it through the vast, hostile emptiness. Until that shield is proven reliable, every other breakthrough, from propulsion to life support, is built on a foundation that cannot endure the journey. That shield alone cannot protect a ship if the materials around it crumble from the inside out. The hull, the electronics, the mechanical joints, and every seal must endure decades of abuse from radiation, micrometeoroid impacts, and the constant cycle of heating and freezing as the ship moves between the warmth of a star and the cold of deep space. Nothing on Earth is built to last that long under those conditions without frequent maintenance. But on an interstellar voyage, there are no repair crews, no spare parts shipments, and no replacement panels waiting in a warehouse. The only way forward is to build a ship that can heal itself. Self-healing materials are one of the most promising answers to this challenge. Researchers on Earth are already developing polymers that can repair cracks automatically. The idea is inspired by the way human skin seals a wound. Tiny capsules filled with a liquid healing agent are embedded inside the material. When a crack forms, it ruptures those capsules, releasing the liquid into the gap. The liquid then reacts with a catalyst also embedded in the material, hardening into a solid that bonds the crack shut. This process can restore most of the original strength, often within minutes. For a spacecraft hull, that means a micrometeoroid impact that would normally create a slow leak can be sealed before the crew even notices a drop in cabin pressure. The technology is not science fiction. It has been tested in coatings for airplane wings and in composite structures for satellites. The European Space Agency has experimented with self-healing materials for space applications, and NASA has studied them for long-duration missions. But for an interstellar ship, the healing system must survive not just 1 or 2 cycles of damage, but potentially hundreds over many decades. The embedded capsules are a finite resource. Once they are used up, the material can no longer repair itself. That is why researchers are also exploring a different approach: vascular self-healing. In this design, a network of tiny channels runs through the material, much like blood vessels in the body. A healing agent circulates through these channels, and when a crack appears, it flows into the damaged area and hardens. The supply can be replenished from a central reservoir, making the system reusable again and again. This kind of vascular healing is still in early research, but it points toward materials that could theoretically repair themselves indefinitely, as long as the reservoir is kept full. The electronics that control every system on the ship face an even more relentless enemy. Cosmic rays can flip a binary bit in a computer chip, turning a 0 into a 1. That single flipped bit might cause a navigation calculation to go wrong, a life support valve to open at the wrong moment, or a fusion reactor to shut down. Over years of exposure, such errors accumulate and can lead to catastrophic failure. Traditional radiation hardening involves shielding sensitive components with heavy materials, or using manufacturing processes that make chips more resistant. Both approaches add mass and cost, and neither is perfect for the extreme conditions of interstellar space. That is why engineers are looking to new semiconductor materials. Silicon carbide is one of the most promising candidates. It can operate at much higher temperatures than ordinary silicon, meaning it can tolerate the heat generated by radiation exposure without degrading. It also has a wider bandgap, a property that makes it inherently less susceptible to the charge disruptions caused by high-energy particles. Diamond-based electronics take this even further. Synthetic diamond, grown in a laboratory, is an exceptional semiconductor with extremely high thermal conductivity and extraordinary resistance to radiation. A diamond-based processor could operate for decades without significant degradation, even in the heart of a cosmic ray storm. The challenge is cost and manufacturing scale. Growing large, pure diamond wafers is still expensive and slow, but research is progressing. Some companies already produce diamond substrates for high-power electronics, and the same technology could eventually be adapted for space-grade computers. Beyond the hull and the chips, the ship's structure itself must be intelligent. Smart materials embedded with fiber optic sensors can detect strain, temperature changes, and impacts in real time. These sensors send data to the central computer, which can pinpoint exactly where damage has occurred and assess its severity. The computer can then activate the self-healing systems in that specific area, or adjust the ship's orientation to reduce stress on a weakened panel. This kind of structural health monitoring is already used in bridges and aircraft on Earth. The leap to an interstellar vessel is a matter of scale and autonomy. The ship must be able to diagnose and repair itself without any human input, because the awake crew may be too small or too busy to tend to every microcrack. Artificial intelligence will analyze the data from thousands of sensors, decide which repairs are urgent, and direct the flow of healing agents to the right locations. But even the most advanced self-healing system has limits. After a century of continuous damage, the material may eventually exhaust its ability to repair. That is why the ship must also carry the means to manufacture replacement parts. A small onboard factory, using raw materials mined from asteroids or harvested from the ship's own waste streams, could print new panels, new seals, or new circuit boards using additive manufacturing. The printer would feed on a stockpile of base elements like aluminum, silicon, and carbon, all carefully recycled from the ship's systems. This is not a far-off dream. The International Space Station already has a 3D printer that produces tools from plastic filament. The next step is printing with metals and ceramics, and the step after that is printing electronics. For an interstellar ship, the printer must be able to produce almost anything, from a replacement valve to a new computer chip, entirely from raw ingredients. That onboard manufacturing capability is a breakthrough that sits at the intersection of materials science, robotics, and recycling technology. Without it, the ship would be like a car with no spare tire, stranded by the first failure that cannot be healed. And the challenge of manufacturing something that complex, far from any supply line, leads directly to the next essential breakthrough: the ability to keep the ship's systems running without failing, for a period longer than any machine has ever operated continuously. No ship can carry every possible spare part across the stars. Even a vessel the size of a city would run out of room long before it could stock all the bolts, circuit boards, valves, and panels that might fail over a century of flight. The only answer is to build the parts as they are needed, on board, from raw materials that are either recycled from the ship's own waste or harvested from asteroids along the way. This is where in space additive manufacturing becomes a critical breakthrough. The International Space Station already proved the concept back in 2014, when a small 3D printer produced its first plastic tool in microgravity. That printer was a simple machine, extruding melted polymer layer by layer, but it demonstrated that the basic physics of additive manufacturing works just fine without gravity pulling the material downward. Since then, engineers have developed printers that work with metals, using high-power lasers or electron beams to fuse fine metal powder into solid shapes. Ceramics and even glass can be printed in similar ways, using binders that are burned away in a later heating step. The challenge for an interstellar ship is to take these laboratory-scale machines and scale them up to produce everything from a simple wrench to a complex rocket nozzle. The printer must be versatile, able to switch between different materials, and it must operate for decades without jamming or degrading. It also needs a steady supply of feedstock. On a ship that already recycles water and air, the waste stream contains metals, plastics, and organic compounds that can be broken down and turned into printer filament or powder. Even the hull itself, if damaged beyond repair, might be melted down and reprinted into a new section. If the ship passes near an asteroid or a moon, it can mine raw metals and silicates directly. A robotic arm could scoop up rock, crush it, and separate useful elements through heating or chemical processes. That feedstock then feeds the printer, which builds whatever the ship requires: a replacement pipe, a solar panel frame, a new antenna dish. The process is slow, but it is patient. The ship has years to manufacture each component. The real breakthrough, however, is not just printing individual parts. It is the ability to print the machines that print the parts. Once a ship can build a new printer from its own recycled materials, it has crossed a threshold. It can now replicate itself, growing or repairing its own manufacturing capacity indefinitely. That is the first step toward a fully self-sustaining starship, one that can not only survive the journey, but also build the tools needed to explore and settle a new world. A single factory that can copy itself is the most powerful tool a civilization could ever build. This is the concept of the von Neumann machine, named after the mathematician John von Neumann, who first described the idea of a self-replicating automaton. Imagine a robotic factory that lands on an asteroid and begins to mine the rock, extract metals and minerals, refine them into raw materials, and then manufacture copies of itself. Each copy then goes to another asteroid, and the process repeats. In a matter of decades, a single seed could grow into a vast network of factories, producing anything from solar panels to rocket engines, all without a single human hand touching the controls. For interstellar travel, this kind of exponential growth is the only way to build the enormous infrastructure needed for a starship. You do not need to launch every component from Earth. You send a small, smart package that can create everything else from the resources it finds along the way. The components of such a system are deceptively simple in concept. A mining robot that digs into rock and separates valuable elements, a chemical processing plant that turns those elements into pure metals or alloys, a 3D printer that shapes those materials into parts, and an assembly arm that puts the parts together into a new copy of the entire factory. Each of these subsystems must be robust, modular, and fully automated. They must work together in a choreographed dance that never stops, because the factory has no tolerance for downtime when the goal is to produce a starship within a few decades. The real challenge is not the hardware, but the software that coordinates everything. Every mining robot must know where to dig and when to stop. Every refinery must adjust its chemistry as the ore composition changes. Every printer must detect errors in its own output and correct them before the part is assembled. This requires a level of autonomy far beyond anything we have today. The control system must be able to handle unexpected failures, adapt to new environments, and optimize its own performance in real time, all without any communication with Earth because the light delay would be hours or days. That kind of intelligent coordination demands a breakthrough in artificial intelligence, a machine mind that can reason about complex systems and make decisions under uncertainty. Without that advanced AI, the self-replicating factory remains a beautiful theory that can never dig its first shovel of asteroid dust. The transition from a single factory to a network of thousands, all working in harmony to build a starship, is the point where automation becomes indistinguishable from life itself. And that leads directly to the next essential breakthrough, an artificial intelligence that can think, learn, and adapt over decades without human guidance. A fixed program cannot survive a century of the unknown, no matter how many contingencies engineers anticipate before launch. The actual journey will throw curveballs that no one on Earth ever imagined. A sensor drifts out of calibration by a fraction of a percent every year, building into a false reading that steers the ship off course. A micrometeoroid punctures a coolant line in a way that the designers never modeled. A crew member develops an unforeseen allergy to a hydroponic crop, and the food system must be redesigned on the fly. Each of these events, taken alone, is manageable. But the cumulative chaos of 100 years in deep space defeats any system that relies on a fixed set of rules. The ship needs a mind that can learn, reason, and adapt without waiting for a software update from Earth, updates that would arrive far too late to matter. That mind is a general artificial intelligence, an AI with the ability to understand any problem presented to it and to generate creative solutions the way a human expert would, but faster and without fatigue. Today's artificial intelligence is powerful but narrow. A system that masters chess cannot drive a car. A system that translates languages cannot diagnose a failing pump. These narrow AIs are like tools, each designed for a single task. They cannot step back, see the bigger picture, and realize that one small anomaly might indicate a cascade of failures hours away. For an interstellar ship, that blind spot is fatal. The AI must possess what researchers call common sense reasoning, the ability to understand cause and effect in a general way, not just within a specific data set. It must be able to transfer knowledge from one domain to another. If it learns how to repair a valve in the water recycling system, it should be able to infer how to repair a similar valve in the fuel system. even if it has never seen that particular component before. This kind of flexible intelligence does not yet exist. The most advanced language models and reasoning systems today still stumble on simple logic puzzles. They can be fooled by subtle changes in wording. They lack a stable understanding of the physical world. They cannot form long-term plans and revise them when conditions change. To reach the level needed for a starship, researchers will need to crack the hardest problem in artificial intelligence: how to build a system that not only processes information but truly understands it. That understanding must be grounded in a model of the world that the ship itself inhabits. The AI should know that a leak means a loss of mass and pressure. It should know that if a repair is delayed, the situation will get worse. It should know that some repairs are worth the risk and others are not. It should even know that the crew has emotional needs and limits, and that pushing them too hard in a crisis could backfire. This last point is crucial because the AI will not operate alone. It will live alongside a small group of human beings who are under extreme psychological strain, isolated from Earth, trapped in a metal can for decades. The AI must communicate with them clearly, honestly, and with a sense of empathy, even if that empathy is simulated. It must be able to explain its reasoning so that the crew can trust its decisions, especially when those decisions involve ethical trade-offs. What happens if a sudden radiation storm strikes and the only way to save the hydroponic garden is to redirect power away from the crew quarters for several hours? The AI must weigh the options, predict the outcomes, and then articulate its choice in a way the crew can accept, even if they disagree. For that to work, the AI must be transparent. Its internal logic must be inspectable, not a black box that spits out answers without explanation. The crew needs to see why the AI believes a certain course of action is best, and they need the ability to override it if they think it is wrong. Designing a system that is both superhumanly capable and completely understandable is a contradiction that current research has barely begun to address. Reliability adds another layer of difficulty. The AI must function without a single failure for the entire journey. A crash, a memory corruption, or a logic error could cascade into a disaster that no human crew could stop in time. That means the software must be written with a level of rigor that surpasses even the most safety-critical systems on Earth. The code must be mathematically verified, proven to be free of certain classes of bugs. The hardware must include triple redundancy, with 3 independent processors voting on every decision. A single hardware glitch is automatically outvoted, and the faulty component is quarantined for later repair. This approach, called fault-tolerant computing, is already used in aircraft and satellites. Scaling it to an entire artificial intelligence that must think and learn over a century is an engineering challenge that has no precedent. And the AI must also be able to repair itself. If a section of its neural network becomes corrupted by cosmic radiation, it must detect the error, isolate the damaged region, and retrain that part of its memory using stored backups. It must do all of this while still keeping the ship safe, a feat akin to performing brain surgery on yourself while running a marathon. The vision of this AI is not a cold, emotionless machine. It is a companion, a guardian, and a collaborator rolled into one. It will be the first entity to greet the crew when they wake from cryogenic sleep. It will teach them how the ship works, guide them through emergencies, listen to their frustrations, and keep them company during the long, dark stretches when there is nothing to see outside but stars. Without it, the ship is a tomb waiting to happen. With it, the ship becomes a living world, capable of responding to any surprise the universe throws its way. And once that mind is functioning, the next question becomes how to keep the humans connected to it, and to each other, over a span of time that erodes memory and identity faster than any machine degrades. That connection must be instantaneous and effortless. The crew cannot spend precious seconds typing commands or scrolling through menus while a crisis unfolds. Their thoughts must flow directly into the ship's mind, and its insights must appear as naturally as their own memories. This is the breakthrough of human-AI symbiosis, a partnership where the line between human cognition and machine intelligence blurs into something new. The ship's AI is not a tool you operate, it is a part of you. The path to this symbiosis runs through a technology called a brain-computer interface. At its simplest, this is a device that reads electrical signals from the brain and translates them into digital commands. Early versions already exist. People with paralysis have used electrode arrays to control robotic arms simply by thinking about moving their own limbs. The signals are decoded by a computer and turned into action. The delay is measured in milliseconds, far faster than any physical movement. For the crew of a starship, that speed could mean the difference between life and death. But reading signals is only half the equation. The true leap is writing signals back into the brain, a two-way conversation. Imagine an augmented reality display that projects information directly into your visual cortex, so you see navigational data floating in the air beside your actual view. Or a neural lace, a mesh of ultra-thin electrodes that threads through the folds of your brain, listening and speaking with every neuron. Projects from companies like Neuralink and agencies like DARPA are working toward exactly this kind of interface. Neuralink has demonstrated a device that can record from thousands of neurons in an animal brain and has received approval for human trials. DARPA has funded research into implantable chips that can restore memory in people with brain injuries. These early steps are crude compared to what an interstellar mission requires, but they point the way. For the crew, the interface must be seamless and safe. They will not have time to train for months before using it. The system must adapt to each individual's unique neural patterns within minutes, perhaps by using machine learning to calibrate itself. Once calibrated, the crew can access the ship's entire knowledge base, all its sensor feeds, all its diagnostic logs, simply by thinking of a question. When a radiation alarm sounds, a crew member does not need to run to a console. The AI pushes a warning directly into their awareness, along with the recommended action. The person reacts before they even consciously process the words. This is not science fiction. In laboratory settings, people have already learned to control cursors and type text using only their thoughts. The next generation of interfaces will add the reverse channel, allowing the AI to send images, sounds, or even abstract concepts into the human mind. The implications for deep space are enormous. Earth will be hours or even days away by radio. The crew cannot wait for advice from mission control. They need the ship's AI to act as an extension of their own intellect, a co-pilot that never sleeps and never forgets. When a tricky repair is needed, the AI can project a step-by-step guide directly into a technician's field of view, overlaying arrows and annotations onto the real world. When a scientific observation requires complex calculations, the AI can handle the math in the background while the human focuses on the question. This partnership removes the bottleneck of typing, reading, and interpreting manual displays. It supercharges human decision-making with machine speed and memory. But this symbiosis demands trust. The crew must feel that the AI is on their side, that its suggestions are reliable, and that their own thoughts remain private when they choose to keep them private. The interface must have an off switch, a way to disconnect and think alone. The AI must also learn the crew's emotional states, recognizing when someone is stressed or tired, and adjusting its communication accordingly. If a crew member is panicking, the AI might simplify its warnings and speak in a calm tone. If they are focused, it might stay silent and only intervene when necessary. This kind of adaptive interaction is far beyond current technology. It requires the AI to model not just the ship's systems but the human mind itself. The reward for solving this challenge is a crew that thinks and acts as one organism. The AI becomes a silent sixth sense, always present, always helping. And once that bond is forged, the crew will face a new limitation that no amount of brain power can overcome: the sheer distance that separates them from Earth. Every message they send will take years to arrive. Every reply will be equally delayed. The human-AI symbiosis will help them cope, but the problem of communication with the homeworld is a barrier that demands its own breakthrough. That distance becomes a wall of silence. Even a radio signal, traveling at the speed of light, takes more than 4 years to cross from Earth to the nearest star. A simple question from a crew member would take 4 years to arrive, and another 4 years for a reply to return. There is no conversation. There is only a slow exchange of letters across an ocean of years. The crew will be isolated in a way no human has ever been isolated before. The challenge of communicating across such a gulf is one of the most profound unsolved problems in interstellar travel. If physics permits no faster than light communication, then the crew must accept a fundamental loneliness. They will send messages to Earth, and their children or grandchildren may receive the answer. That is the reality most mission planners assume. But what if a breakthrough in physics changed that? What if we could send information faster than light? The most tantalizing possibility involves quantum entanglement. When two particles are entangled, measuring one instantly affects the other, no matter how far apart they are. Albert Einstein called this spooky action at a distance, and it is real. Scientists have demonstrated entanglement over hundreds of kilometers. The catch is that while the correlation is instant, you cannot use it to send a message. The act of measuring one particle gives you a random result, not a controlled signal. You cannot choose what that result conveys. There is no way to encode information on top of the entanglement without breaking the very link that makes it special. Current physics is clear: quantum entanglement cannot transmit information faster than light. It is a beautiful, mysterious phenomenon, but it is not a phone line to the stars. Unless our understanding of quantum mechanics is incomplete, and there is a deeper layer of reality that allows information to flow through the entanglement in a way we have not yet discovered, but that is pure speculation. No reputable theory today predicts such a capability, so the practical approach for any near-term interstellar mission is to accept the delay and design around it. The ship will send bursts of data using highly focused laser beams. A laser communication system can pack enormous amounts of data into a narrow cone of light. It is far more efficient than radio. NASA has already demonstrated laser links from the moon, sending high-definition video at speeds of hundreds of megabits per second. For an interstellar probe, the same concept would work, but the beam would need to be aimed with extreme precision over distances of trillions of miles. The receiving station on Earth would be a large telescope array, fine-tuning its aim to catch the faint flicker of photons from a moving ship. The data rate would drop sharply with distance, but even a trickle of bits per second could carry vital information: images of the destination star system, telemetry from the ship, health reports from the crew. The ship would store all its data and send it in periodic bursts, perhaps once a month or once a year. When its laser array is pointed toward Earth, the crew would receive bursts from home in the same way. This is not a conversation, it is a correspondence with years of lag. The ship would operate almost entirely autonomously. The AI would handle all routine decisions, all emergencies, all navigation. The crew would be trained to work without real-time guidance from Earth. They would rely on their own judgment, the AI's advice, and the knowledge they brought with them. This autonomy is itself a breakthrough that we have already touched on. Without it, the mission is impossible, but a true faster-than-light communication system would change everything. It would turn the ship from an isolated outpost into a connected part of a larger civilization. the crew could consult experts on Earth in real time. They could share their discoveries instantly. They could even receive software updates or new medical knowledge as it was developed. The psychological impact would be enormous. The crew would never truly be alone. They would remain part of the human conversation, even while crossing the void. Such a breakthrough would require a new understanding of physics, perhaps a way to exploit wormholes or to manipulate the quantum vacuum in ways we cannot currently conceive. Most scientists doubt it is possible, but the history of science is filled with discoveries that overturned what was thought to be impossible. For now, the assumption is that the crew will be cut off from Earth, relying on their own intelligence and the AI's companionship. But if that assumption ever falls, it will unlock a future where the stars themselves become a neighborhood, not a destination for the isolated. That silence across the void makes every single move the ship makes count with terrifying precision. A navigational error of just 1/10,000th of a degree at launch would cause the vessel to miss its target star system by millions of miles after decades of travel. There is no room for guesswork, no second chance to correct a mistaken reading. The ship must know exactly where it is and exactly where it is going at every moment for the entire voyage. This requires a breakthrough in precision astrometry, the science of measuring the positions and motions of stars with incredible accuracy. On Earth, astronomers already map nearby stars to within a few millionths of a degree using instruments like the European Space Agency's Gaia satellite. But Gaia looks outward from a fixed point near Earth. A starship will be moving at a significant fraction of the speed of light, and that motion distorts the apparent positions of stars. The light from stars ahead will shift toward the blue end of the spectrum, while stars behind shift red. The angles between stars change subtly as the ship accelerates and decelerates. The ship's navigation system must constantly recalculate its position by comparing the observed star field against a deep onboard catalog that accounts for all those relativistic distortions. To date, the best star catalogs cover hundreds of millions of stars, but they are calibrated for Earth's reference frame. For an interstellar mission, the catalog must be extended and corrected for the ship's unique relativistic frame of reference. That means the AI must carry a model of the galaxy that updates continuously as the ship moves. It is not enough to know where a star is today. You must know where it will be when you arrive, because the star itself is moving through space at tens of kilometers per second. Over decades, that motion adds up to a shift that can erase all your careful calculations. The solution lies in a navigation system that does not rely on stars alone. Pulsars, the rapidly spinning remnants of exploded stars, emit regular pulses of X-rays with a precision that rivals atomic clocks. Each pulsar has a unique pulse pattern, like a fingerprint. By detecting these pulses from a moving spacecraft, you can triangulate your position in 3 dimensions with extreme accuracy. This is essentially a galactic GPS system, and NASA has already tested the concept with an instrument called NISA, the Neutron Star Interior Composition Explorer, mounted on the International Space Station. NISA demonstrated that X-ray pulses from multiple pulsars could be used to determine a spacecraft's position within a few kilometers, even at the distance of Earth orbit. For an interstellar ship, the same technique will work across light years. The ship's X-ray detectors will point at a set of known pulsars, measure the arrival times of their pulses, and compare those times with a model of each pulsar's clock. The differences reveal the ship's position and velocity in real time, with no need for any communication with Earth. But pulsar navigation alone is not enough. The ship must also be able to detect and track the destination star system long before it gets there. As the ship approaches its target, the stars in that system become resolvable as individual points of light. The ship's telescopes will watch for the subtle wobble of the star caused by orbiting planets, or the dimming when a planet crosses its face. These observations will refine the trajectory, ensuring the ship does not overshoot or crash into an uncharted world. The challenge is that the entire system has never been seen up close before. The ship is navigating into the unknown, relying on data gathered from light years away that may be years old. The AI must combine all the data from astrometry, pulsar navigation, and telescopic observations into a single coherent picture, and then update the course instantly as new information arrives. This leads to a critical need for autonomous course correction algorithms. The ship will experience tiny, unpredictable nudges from gravity, from the faint pressure of sunlight, and from the subtle drag of interstellar gas. These nudges accumulate over years, pulling the ship off its ideal path. The AI must detect these deviations early and fire the ship's thrusters in brief, efficient bursts to bring it back on track. The whole process must happen without any human intervention because the crew may be asleep or unreachable. The AI must be able to predict the future trajectory, calculate the minimal correction, and execute it perfectly, all while conserving fuel for the braking maneuver at the destination. The final piece of this navigation puzzle is mapping the destination system in advance. Before the ship enters the system, it must know the orbits of all major planets, the location of asteroids, and the presence of any planetary rings or debris fields. A high-speed collision with a pebble-sized asteroid at the ship's velocity would be catastrophic. The ship will scan the system for years before arrival, using its telescopes to build a detailed gravitational model. It will then plan a safe approach trajectory, perhaps using the gravity of a large planet to slow down. That gravity assist, a technique already used in our solar system, becomes a precision maneuver that relies on every previous measurement being perfectly accurate. Without precision astrometry and navigation, the ship is a blind arrow shot into the dark. With it, the ship becomes a guided missile, threading the eye of a needle across trillions of miles. The breakthrough here is not just better instruments, it is a complete system of measurement, prediction, and control that works perfectly without any external reference point. And once that system is proven, the next step is to see the destination not as a single point of light, but as a complex world waiting to be explored. That requires mapping the system in detail before the crew ever sets foot on a new planet. That mapping must be done from afar, long before the ship arrives. The crew cannot afford to fly blind into an unknown system. They need to know not just the number of planets and their rough orbits, but the exact size, composition, weather patterns, and even surface details of each world. They need to know which world has a breathable atmosphere, which has liquid water, and which hides a field of jagged boulders that would tear a landing craft to pieces. This information must be gathered from light years away, using telescopes that dwarf anything we have ever built. The most promising tool for this job is the solar gravitational lens. The idea takes advantage of a quirk in Einstein's general relativity. When light from a distant object passes close to a massive body like the sun's gravity bends that light, acting exactly like a giant lens. If you place a telescope at the right point in space, roughly 550 astronomical units from the sun, far beyond the orbit of Pluto, the sun's gravity will magnify any light coming from behind it. An astronomical unit is the distance between Earth and the Sun, so that is a long way out. But from that vantage point, a telescope could resolve surface features on an exoplanet tens of light years away. It could see continents, oceans, cloud patterns, and even the glow of city lights if any exist. For an interstellar mission, that kind of detail is worth the journey just to build the observatory. A spacecraft equipped with a solar gravitational lens telescope would be launched decades before the main Starship. It would travel to that distant focal point, taking perhaps 30 years even with advanced propulsion. Once there, it would begin a painstaking survey of the destination star system. It would watch the planets as they orbit, measuring their rotation rates, mapping their seasons, and detecting the chemical fingerprints of their atmospheres. A world with abundant oxygen and methane in its air would be a strong candidate for life. A world with massive dust storms or volcanic activity might be too dangerous. The telescope would also identify potential hazards like asteroid belts or wandering comets that could threaten the approaching ship. All this data would be beamed back to Earth and then to the starship as it prepares to leave the solar system. The crew would have a detailed atlas of the target system long before they ever accelerate toward it. They would choose their destination not based on guesswork but on solid evidence. They would know which planet offers the safest landing site, which moon has the right minerals for fuel production, and which orbit provides the best protection from radiation. This pre-flight reconnaissance transforms a blind leap into a calculated approach, and once the starship finally crosses the threshold into the new system, all that knowledge will guide the next and most dangerous phase, the slow, careful insertion into orbit around an alien world. That detailed atlas transforms the approach from a blind leap into a calculated arrival. Yet one problem remains. The ship arrives screaming in at a significant fraction of the speed of light. Slowing down demands as much energy as the acceleration did, and that energy must come from somewhere. Without a braking system, the starship will simply blast through the target system in a matter of hours, leaving behind only a blur of useless data. The crew would watch their destination streak past the windows, never able to stop and explore. This is why deceleration is not just an afterthought. It is one of the hardest engineering challenges in the entire mission. The most straightforward method is to reverse the acceleration process. If the ship used a light sail and a laser array to speed up, it can use the same sail to slow down by catching the light from the destination star. The sail, now facing the star, acts like a giant brake, using the star's own photons to push against the ship's motion. This technique, called photon braking, requires a sail that is precisely oriented and incredibly reflective. The star's light is far weaker than the focused laser beam that accelerated the ship, so the braking would take years or even decades. The sail must survive constant exposure to intense radiation and heat without degrading. Any imperfection in the sail's surface would cause it to absorb energy instead of reflecting it, turning the sail into a fragile oven that would quickly melt. Another approach is magnetic braking. Many stars, including our own Sun, generate powerful magnetic fields that extend far into space. A spacecraft equipped with a large superconducting loop could generate its own magnetic field that interacts with the star's field. The interaction creates a drag force, slowing the ship down without any propellant. The energy of motion is transferred into the star's magnetic field, heating it slightly. This method is elegant, but it requires an enormous magnetic loop, perhaps kilometers in diameter, and the ability to cool its superconductors for years. The loop would also experience tremendous mechanical stress as it cuts through the star's magnetic environment. Any failure in the magnetic system would leave the ship racing past its target with no way to stop. A third idea uses the thin outer atmosphere of the star itself. Aerobraking is a technique used by spacecraft in our own solar system, where a probe dips into a planet's atmosphere to shed speed using friction. For an interstellar ship, the same concept could be applied to the destination star. The ship would dip into the star's outer corona, the extremely hot but very thin outer layer, where friction with the sparse gas would gradually slow it down. The problem is heat. The corona can reach millions of degrees, but it is so thin that the actual heat transfer is manageable if the ship passes through it quickly enough. However, the ship must be designed with a heat shield that can handle the intense radiation and magnetic fields of the stellar atmosphere. Even a brief pass would subject the hull to extreme thermal shock, and the ship would need to repeat this maneuver many times to shed enough velocity without burning up. Each pass would shave off a little more speed, slowly pulling the ship into a stable orbit around the star. The whole process could take years. Each of these methods places enormous stress on the ship's structure and thermal management systems. The deceleration phase will be the most violent and hazardous part of the entire journey. The crew, if awake, would be subjected to sustained high G-forces as the ship brakes, or they might remain in suspension while the AI manages the complex ballet of slowing down. The navigation system must execute each braking maneuver with extreme precision, because any error could send the ship into the star or fling it out of the system forever. The AI must constantly recalculate the optimal trajectory, balancing the rate of deceleration against the heat load and the structural limits of the ship. Once the ship is finally slowed to a reasonable speed, it can enter orbit around a planet or moon and begin its exploration. But before any of that deceleration can even be attempted, the ship must survive the journey itself. And that journey is not through empty space. It is through a thin but dangerous fog of interstellar dust and debris, particles that could punch through the hull like bullets at relativistic speeds. That unseen hazard is the next breakthrough that must be solved before any starship can hope to arrive intact. That interstellar fog of dust and debris becomes a nightmare at high speed. When a starship pushes to even 10% of the speed of light, every grain of dust it encounters transforms into a tiny bomb. A particle the size of a grain of sand, something that would be harmless at orbital velocities, strikes the hull with the energy of a small explosive charge. The impact vaporizes both the dust and a chunk of the ship's outer skin, creating a crater and sending a shock wave through the structure. Over decades, a steady drizzle of these microscopic projectiles would erode the hull, puncture critical systems, and eventually disable the vessel long before it reached its destination. The only answer is an active defense system that can intercept and neutralize these particles before they hit. One concept uses a cloud of plasma, a diffuse, electrically charged gas that surrounds the ship like a protective bubble. When a dust grain enters the plasma cloud, it becomes charged and is then deflected by magnetic fields away from the hull. The plasma must be dense enough to interact with every incoming particle, yet thin enough not to drag on the ship's motion. Maintaining that balance over years is a continuous power and material challenge. Another approach is a sacrificial shield, a thin layer of material placed at a safe distance ahead of the main hull. The shield takes the hits, absorbing impact after impact, and is slowly consumed. It works like the ablative heat shield on a re-entry capsule, but instead of one intense burn, it must survive thousands of small strikes. The shield would need to be thick enough to last the entire journey, which adds mass, and it must be replaced or renewed if damaged. Some designs propose using multiple layers that can be ejected and discarded one by one as they wear out. A more elegant solution uses a laser mounted on the ship's nose. A forward scanning system detects any dust grain or small rock in the path, and the laser fires a brief, powerful pulse that vaporizes the particle before it can strike. The vaporized material expands into a harmless puff of gas that the ship passes through a moment later. This method requires a laser with extremely fast targeting and enough energy to vaporize hundreds of particles per second during the densest parts of the journey. The laser itself must be rugged and reliable, and it needs a constant supply of power, which adds to the ship's energy budget. There is a classic idea from the 1960s called the Bussard ramjet that tried to turn this problem into a solution. The concept uses a giant magnetic scoop that collects interstellar hydrogen as the ship moves, feeding it into a fusion reactor for fuel. In theory, that magnetic field could also deflect dust, but the reality is far more complex. The interstellar medium is incredibly sparse, and the scoop would have to be enormous to gather enough hydrogen to be useful. The drag created by sweeping up that material would actually slow the ship down more than the fusion energy could compensate for, especially at the speeds needed for interstellar travel. Most modern assessments conclude that the Bussard ramjet is not efficient enough to be practical, and the magnetic scoop, while it might deflect some dust, would face the same structural and energy challenges as other active shielding systems. No single method is perfect on its own. A robust interstellar dust mitigation system will likely combine several approaches. A sacrificial outer layer handles the majority of tiny impacts. A plasma or magnetic field diverts larger particles that might punch through, and a forward laser vaporizes the biggest threats that the other systems cannot stop. The entire system must be redundant, self-monitoring, and able to operate for decades without maintenance. If even one particle gets through at the wrong place, it could rupture a critical pipe, disable a computer, or breach a crew compartment. Surviving the dust is a necessary condition for reaching another star, but even if the hull remains intact and the engines hum perfectly, the greatest fragility resides inside the ship, the human body and mind. Maintaining crew health over decades of isolation, confinement, and zero gravity is a challenge that touches every other system on the vessel, and that is where the next set of breakthroughs must focus. But what if the human body could be redesigned from within before the journey ever begins? The crew of a starship will face dangers that no human has ever endured for so long. Radiation that slips past the best shields, bones that weaken despite spinning habitats, minds that fray under decades of isolation. Instead of trying to build stronger walls around a fragile human, what if we changed the human itself? This is the breakthrough of genetic engineering for space adaptation, the idea that we can rewrite our own DNA to make astronauts resistant to the very conditions that threaten them. The path starts with simple tweaks borrowed from nature. There is a bacterium called Deinococcus radiodurans that can survive radiation doses thousands of times higher than what would kill a human. It does this by carrying multiple copies of its genome and by having an extremely efficient DNA repair system. Researchers have already identified the genes responsible for that repair and have inserted them into other organisms in the lab. The next step is to introduce similar genes into human cells, giving them the ability to stitch broken DNA strands back together far faster than our natural machinery allows. Other species offer other gifts. Tardigrades, microscopic animals sometimes called water bears, produce a unique protein that protects their DNA from radiation damage. When that protein is added to human cells in a petri dish, the cells survive more than 40% more radiation. The same principle could be applied to an entire astronaut. A single injection of a harmless virus carrying the tardigrade gene could give every cell in the body an extra layer of protection. For the low-gravity environment, genetic changes might help prevent bone loss by altering how bone cells respond to mechanical stress. Some animals, like bears during hibernation, naturally maintain bone density even while inactive for months. Their genetic programming could guide human cells to do the same during years of weightlessness. Hibernation itself is another trait worth borrowing. Black bears can drop their body temperature, slow their heart rate to just a few beats per minute, and survive without food or water for 5 to 7 months. If humans could be induced to enter a similar state on demand, the savings in food, water, and oxygen would be enormous. The crew would not need to be awake for the long middle portion of the journey. They would sleep through decades, guarded by the AI, with their metabolism barely ticking over. Scientists have already identified the molecular switches that trigger hibernation in animals, and the hope is to create a drug or a genetic modification that lets us flip that switch ourselves. Taken together, these modifications would produce a crew member who is no longer a baseline human. They would be a purpose-built astronaut, designed from the genetic level to survive the journey. And that raises a question that goes beyond engineering. At what point does a person stop being human? If we add genes from bacteria, from tardigrades, from bears, and from other species, the resulting individual may look human, but their biology is a patchwork of borrowed parts. Do they still possess the same moral status, the same rights, the same sense of identity as someone born without those changes? These ethical concerns are not theoretical. They will be debated long before the first modified astronaut is conceived. Some people will argue that we have no right to alter the human germline, that we are crossing a line that should never be crossed. Others will say that if we have the power to save lives and make the journey possible, we have a duty to use it. The debate will touch on deep questions about what it means to be human, about the value of natural evolution, and about the kind of future we want to build. But the ship will wait for no debate. If the mission is to happen, a generation of purpose-built astronauts will need to exist. They will be raised, trained, and modified from birth for a single purpose. Their entire lives will be a preparation for a voyage that ends in a new star system. That sense of purpose, combined with the psychological weight of knowing they are not quite like the humans they left behind, creates a new set of challenges. It is one thing to engineer a body that can survive the void. It is another to engineer a mind that can endure the loneliness of it. The longest continuous human settlement ever built is not a city or a country. It is the International Space Station, which has hosted rotating crews for more than 2 decades, but no single person has lived there for more than a year. A generation ship demands something never attempted, a society that must remain stable for centuries without the constant input of new citizens from Earth. The people who launch will never see the destination. Their children will not see it either, nor their grandchildren. Only descendants many generations removed will finally step onto alien soil. The social structure that carries them across that gulf must be designed with as much care as the life support system, because a rebellion, a civil war, or even a slow collapse of trust would doom the mission just as surely as a hull breach. History offers uncomfortable lessons. Closed communities on Earth, from monasteries to Antarctic research stations, have struggled to maintain cohesion over long periods. Biosphere 2, a sealed ecological experiment in Arizona during the 1990s, hosted 8 people for 2 years. Within months, the group fractured into factions. Tensions arose over food distribution and work assignments, and the experiment ended early with lingering bitterness among the crew. The lesson is clear: psychological and social pressures grow more intense as isolation deepens and the possibility of leaving disappears. On a generation ship, there is no exit. No one can quit and fly home. Every conflict must be resolved internally, or it festers for decades. That means the ship must have a form of governance that feels legitimate to every person on board. Some proposals lean toward a rotating council of elected representatives, with terms of service that prevent any single individual from accumulating power. Others suggest a system modeled on consensus-based communities, where major decisions require broad agreement. The key is that the system must be transparent and fair. A hidden hierarchy would breed resentment. The rules must be known by all, and there must be a clear process for changing them when circumstances evolve. Children born on the ship will grow up knowing only that world. Their loyalty will be to the ship and its mission, but that loyalty must be earned, not assumed. Family structures on a generation ship will look different from those on Earth. Traditional nuclear families may be too small to provide the social support needed over decades. Instead, the ship might organize into extended kinship groups or clans that share childcare, work, and emotional support. Parenting becomes a community responsibility, with experienced elders teaching the young not just reading and math, but the history of their journey and the purpose of their destination. Education must go beyond facts. It must instill a deep sense of pride in the mission, a feeling that each child is part of something larger than themselves. Stories of Earth, of the homeworld left behind, will be passed down like ancient myths. The ship itself will become a living museum of human culture, preserving art, music, and traditions that might otherwise be lost in the focus on survival. Cultural traditions are the glue that holds a society together through change. The ship must create rituals that mark the passage of time and reinforce shared identity. Perhaps an annual celebration on the anniversary of launch, a holiday where everyone gathers in the central hub to watch a recording of Earth from the day they departed. Or a ceremony when a child reaches adulthood, symbolizing their acceptance into the crew of the next generation. These rituals give meaning to the otherwise monotonous days of life in a metal can. They remind everyone that they are not just passengers, they are the custodians of a legacy that began thousands of years before them, but no amount of tradition can prevent conflict entirely. People will disagree about resources, about leadership, about the direction of the mission. That is why the ship must have built-in conflict resolution protocols that are swift and fair. One approach is to designate a group of trained mediators, individuals who have no stake in the disputes they resolve. Another is to create a formal process for airing grievances with recorded hearings and binding decisions. The worst outcome is for a disagreement to simmer for years, poisoning relationships and splitting the community into factions. The social system must include escape valves, ways for people to express frustration without tearing the whole structure apart. Some designs even include a designated quiet room where anyone can go to scream or cry without judgment. The study of isolated communities on Earth, particularly Antarctic research stations that overwinter with small crews, has shown that personality conflicts are the most common cause of mission failure. Technical failures are rare compared to human ones. The best teams are not necessarily the most skilled individuals, but the ones whose personalities complement each other. That means the selection of the initial crew must go far beyond technical skills. Psychologists will evaluate candidates for emotional stability, flexibility, and the ability to live in close quarters without dissolving into conflict. The crew must be a balanced mix of thinkers and doers, introverts and extroverts, leaders and followers. Children born on the ship will inherit that balance, but they will also develop their own personalities. The challenge is to raise them in an environment that fosters mental health and resilience despite the lack of natural horizons, the absence of seasons, the unending sameness of the view outside the windows. Virtual reality can help, projecting landscapes and forests and cities onto the walls of common areas, but the deepest need is for meaningful relationships with others. The social fabric of the ship must be woven with care, thread by thread, over generations, and that fabric, no matter how carefully woven, will fray under the weight of time. The next breakthrough is not about architecture or governance, but about the inner lives of the people themselves. A ship that lasts centuries must also heal the wounds that isolation inflicts on the mind. That inner life can be the most fragile system on the ship. A human mind did not evolve to spend decades inside a metal tube with the same few faces, the same recycled air, the same unchanging view of stars that never seem to move. The deepest threat to an interstellar crew is not radiation or micrometeoroids. It is the slow erosion of hope that comes from knowing you cannot step outside, cannot feel rain on your skin, cannot walk more than a few hundred meters in any direction. Every study of long-term isolation, from submarines that patrol for months to Antarctic stations that endure year-long darkness, shows that the human psyche has limits. After a certain point, even the most resilient individuals begin to show signs of strain, irritability, withdrawal, depression, and a loss of meaning. On a starship, there is no emergency evacuation. The crew must live with that strain for decades, and they must do so without the sensory richness that anchors mental health on Earth. The answer is not simply to select the most stoic astronauts. It is to build an environment that actively supports psychological well-being through design, technology, and routine. Virtual reality will be one of the most important tools. A crew member can put on a lightweight headset and instantly be standing in a forest, on a beach, or in a bustling city from their memory of Earth. These environments must be rich, interactive, and updated regularly to prevent boredom. They can include social spaces where crew members meet in a simulated park, or solo retreats where they watch a sunset over an ocean that exists only in code. The key is variety. The same simulation repeated too often loses its power, so the ship's AI will generate new landscapes, new weather patterns, and new experiences over the years. Counseling will not be left to human therapists alone. An artificial intelligence trained in psychotherapy can be available at any hour without judgment to listen and guide. It will recognize signs of emotional decline before the person themselves does by analyzing speech patterns, sleep cycles, and social interactions. It can gently suggest a conversation, a change in routine, or a visit to the virtual world. This AI companion must be trusted, which means it must maintain strict confidentiality and never use the information against the person. Pharmacological mood management will also play a role, carefully monitored to avoid dependency. Medications that ease anxiety or lift depression can be administered in controlled doses, but the ship cannot carry a pharmacy that lasts for generations. Instead, the crew will rely on a compact drug synthesis system that can produce common psychiatric medicines from basic chemical stocks, directed by the AI's recommendations. The design of the physical spaces on board is just as critical. Every corridor, every cabin, every common area must be crafted to counteract the crushing sameness of a metal world. Colors can change with lighting, wall panels can be swapped for different textures or imagery. Privacy must be absolute. Each crew member needs a space that is truly their own, a personal sanctuary where no one else can enter without permission. In a vessel where you are never more than a few meters from another person, that private bubble is a lifeline. The layout must also include unexpected nooks, curved passages that hide the vessel's true size, and windows that look out onto star fields or, when the ship passes through empty space, onto a simulated Earth projected on a screen. The lessons from submariners and astronauts are clear. The most dangerous time is not the first month but the third, the sixth, the 10th year, when the novelty has worn off and the reality of the situation sinks in. That is when the interior architecture of the ship becomes as crucial as its propulsion. A ship that feels like a prison will produce prisoners. A ship that feels like a home, a world, a sanctuary, will nurture the resilience needed to reach another star. Yet no amount of psychological design can compensate for a single catastrophic hardware failure. A spacecraft that crosses trillions of miles to another star has no towing service, no rescue ship, no spare parts depot waiting at the halfway point. If a single critical component fails, the entire mission folds into a silent coffin drifting through the void. Every system, from the fusion reactor to the water recycler, must be built with a philosophy that goes far beyond ordinary reliability. That philosophy is called fail operational design, and it is the difference between a ship that survives and a ship that perishes. In aviation, a commercial airliner is designed with triple redundancy for its most critical systems. 3 separate hydraulic lines, 3 independent flight computers, 3 sources of electrical power. If one fails, the second takes over seamlessly. If the second fails, the third is still there. The aircraft can lose 2 of everything and still land safely. That standard is already demanding, but an interstellar ship must go even further. A failure that strands the ship in deep space is not an inconvenience. It is a death sentence extended over decades, so redundancy cannot be limited to just 1 or 2 backups. It must be woven into the very fabric of the vessel. Consider the propulsion system. Whether it relies on fusion or antimatter, the engine is the heart of the ship. If it stops working, the vessel becomes a derelict. The solution is to have not one engine but multiple independent thruster units, each capable of providing enough thrust to complete the mission, albeit at a slower pace. If one unit fails, the others compensate. If fuel lines rupture, separate storage tanks with their own valves and pumps can be isolated and rerouted. The control software must be able to detect a failing component in milliseconds, shut it down, and redistribute the load without any human intervention. This is not just backup, this is graceful degradation, where the ship continues to function at a reduced capacity rather than collapsing entirely. Life support is the most unforgiving system of all. A human being can survive without food for weeks, without water for days, but without oxygen for only minutes. The air recycling system must have at least 3 independent loops, each fed by a different power source, each capable of sustaining the entire crew. The water purification system must be similarly duplicated. A single leak in a pipe cannot be allowed to drain the entire reservoir. Instead, the system should be divided into multiple sealed sections, each with its own sensors and shut-off valves. If one section fails, the others remain sealed and operational. The crew will lose a fraction of their water supply, but they will not lose it all. The ship's central computer, the mind that runs everything, must be designed with what engineers call fault tolerance. 3 or more processors run the same calculations simultaneously, constantly comparing their results. If one processor gives a different answer than the other 2, it is immediately marked as faulty and taken offline. The remaining 2 continue, and if one of them later fails, the last remaining processor still runs the ship while the AI works to repair or replace the failed units using the onboard manufacturing system. This architecture, known as triple modular redundancy, is already used in spacecraft like the Space Shuttle. For an interstellar mission, it must be extended to every subsystem, from navigation to medical monitoring. Nuclear submarines offer another powerful lesson. These vessels operate for months without surfacing, in an environment where a single leak can be catastrophic. Submarines are built with multiple watertight compartments, each capable of being sealed off from the others. If one compartment floods or catches fire, the rest of the submarine remains safe. The crew can retreat, isolate the problem, and survive until the situation is resolved. A starship must adopt the same compartmentalization, not just for air and water, but for every critical resource. Energy storage, food stores, spare parts, all must be distributed across the ship so that no single explosion, fire, or breach can deprive the entire crew of a necessity. But there is another layer to redundancy that is often overlooked: redundancy of skills. A crew that relies on a single expert for navigation, a single doctor, or a single engineer is vulnerable. If that person becomes incapacitated, the knowledge leaves with them. That is why every critical skill must be shared among at least 2 crew members, and ideally more. The ship's AI must also store detailed procedural knowledge accessible to anyone, so that a cook can learn to repair a pump in an emergency. Cross-training is not a luxury. It is a survival strategy, yet even with the most thorough redundancy, there is one failure that no amount of backups can fix: the failure of the destination itself. What if the star system that looked so promising from Earth turns out to be hostile? What if the planets are barren, the atmosphere toxic, the radiation levels lethal? The ship must carry a contingency plan for that scenario. It might be a second target star system, a backup destination that can be reached by altering the trajectory during the long cruise phase. Or it could be the ability to continue drifting, using the ship's resources to sustain the crew for additional generations while they search for a habitable world. Some designs include a self-contained survival module that can detach and land on a marginal world, using onboard manufacturing to build a permanent settlement even under harsh conditions. This is not giving up on the primary goal. It is accepting that the universe is unpredictable and that a vessel that cannot adapt is a vessel that will eventually become a tomb. The ultimate failsafe is the ability to change the plan. Surviving the crossing is only half the victory. After decades of travel through the void, the crew arrives at a star system that has never been touched by human hands. Their ship is battered, their supplies are low, and Earth is light years away. No cargo vessel will arrive with fresh water or replacement parts. Everything they need to survive and eventually establish a settlement must come from the worlds and rocks that orbit the destination star. This is where in-situ resource utilization becomes not just a convenience but the absolute foundation of survival. In-situ means on-site, and the principle is brutally simple: use what you find. The ship itself may have carried enough supplies for the journey, but those supplies are nearly exhausted. The colonists must harvest water, oxygen, building materials, and fuel directly from the environment around them. The first and most precious resource is water. Ice is common in the outer reaches of most star systems, locked in the shadows of craters or frozen into the crust of moons and asteroids. If the destination system has a planet with a thin atmosphere or a surface covered in ice, the colonists will send robotic miners to dig it up. That ice is then melted and purified. But water is not just for drinking. Split it apart with electricity in a process called electrolysis, and you get two gases, hydrogen and oxygen. Oxygen is breathable air. Hydrogen becomes rocket propellant, and if you combine that hydrogen with carbon dioxide, which can be pulled from a planet's atmosphere or even from the ship's own exhaust, you get methane and water through the Sabatier reaction. Methane is an excellent fuel for landing craft and surface vehicles. NASA has been testing exactly these processes for years under its Mars ISRO plans. The agency envisions a future where a small chemical plant lands on Mars before the astronauts do, producing oxygen from the thin carbon dioxide atmosphere. The Mars Oxygen In-Situ Resource Utilization Experiment, or MOXIE, rode aboard the Perseverance rover and successfully converted Martian carbon dioxide into oxygen. The machine was small, only about the size of a car battery, but it proved that the chemistry works in a real planetary environment. Scaling that up to support a crew is a matter of engineering, not physics. The colonists will also need building materials. They cannot launch concrete and steel across light years. Instead, they will mine regolith, the loose rock and dust that covers the surface of most planets, moons, and asteroids. Regolith can be processed in simple furnaces to extract metals like iron, aluminum, and titanium. Silicates can be baked into bricks or melted into glass. Some advanced proposals even use microwaves to sinter the dust into solid paving blocks, creating landing pads and roads without any imported binder. A 3D printer fed with melted regolith can construct habitats, storage tanks, and structural supports layer by layer. These machines are already being tested on Earth, printing entire buildings from simulated lunar soil. The challenge is making them robust enough to operate for years without human supervision on an alien world. The most ambitious colonists will not rely on mining only what is on the surface. They will target asteroids, small rocky bodies that are rich in metals and water. A single asteroid 100 meters across could contain more platinum group metals than the entire annual production on Earth. It also holds enough water ice to fill a small lake. A robotic mining craft would land on the asteroid, crush the rock, and heat it to release the water. The water is electrolyzed into hydrogen and oxygen, and the metals are refined on the spot. This transforms the asteroid into a fuel depot and a source of raw materials rolled into one. But the true power of in-situ resource utilization is not just about survival. It is about preparation. Before the first human ever sets foot on a new world, the ship's AI can launch a fleet of robotic factories ahead of the crew. These pre-positioned machines land on the target world and begin working immediately. They mine ice, they extract oxygen from the atmosphere, they manufacture fuel. They build a landing pad, they construct a simple habitat. All of this happens while the crew is still years away, traveling through the dark. By the time the starship finally arrives, the infrastructure for survival is already waiting. The colonists step off the ship into a world that has been prepared for them, not a barren wilderness. That is the breakthrough that turns a desperate landing into a confident arrival. And once the first foothold is established, the next challenge becomes how to multiply that foothold into a self-sustaining civilization that can thrive without any support from Earth at all. The first human footprint on that distant world will be preceded by 1,000 tireless robots. Decades before the crew even wakes from the final sleep cycle, a fleet of machines will have already landed, drilled, tested, and built. They will work in utter silence under a sky lit by an alien sun, with no human hand to guide them through the daily challenges of a foreign world. This is the breakthrough of automated robotic precursors, and without it, the crew would arrive blind, vulnerable, and dangerously unprepared. The reason is painfully simple. Light takes years to travel between the stars. If the ship's AI detects an unexpected boulder field on the landing site, it cannot send a message to Earth and wait for advice. By the time the answer comes back, the ship will have already arrived. So the robots sent ahead must be completely self-sufficient. They must be able to survey the terrain, analyze the composition of the soil, test the stability of the ground, and make decisions about where to build, all without a single command from home. This requires a level of autonomy far beyond anything we have launched so far. Imagine a swarm of small probes, each no bigger than a suitcase, released from a carrier spacecraft as it approaches the target star system. These probes spread out like seeds, each one programmed to map a different region. Some are orbiters that photograph every kilometer of the surface from above, creating a detailed atlas of craters, mountains, and plains. Others are landers that touch down on promising sites, scoop up samples, and analyze them with onboard instruments. They sniff the air for toxic gases, measure the radiation levels at ground level, and listen for seismic activity that might reveal hidden dangers. All of this data is beamed back to the carrier, which compiles it into a single living map of the new world. But mapping is only the first step. The real work begins when the construction drones arrive. These are larger robots, perhaps the size of a small car, equipped with tools and manipulators. Their job is to prepare the landing site for the crew. They clear boulders, level the ground, and lay down a landing pad made from melted local rock. They dig trenches for power cables and water pipes. They assemble a simple habitat, inflating a dome or stacking printed blocks, long before any human ever breathes the local air. Some drones tow mobile factories that can extract water from the ice and split it into oxygen and hydrogen, filling storage tanks for the crew to use the moment they step off the ship. The most impressive part is the coordination. These robots are not individually remote controlled. They are a distributed network, each one aware of what the others are doing. If one drone breaks down, another moves in to finish its task. If a survey probe discovers a richer source of water a kilometer away, the construction drones recalculate their route and reroute the pipeline. The entire operation runs on a decentralized intelligence that can adapt to surprises without any central command. This is not a single master computer giving orders. It is a colony of independent machines that share information and negotiate priorities among themselves. Communication with the carrier ship, which may still be decades away, is limited to occasional status updates. The robots cannot wait for instructions that will arrive years too late, so the onboard algorithms must be robust enough to handle every contingency that the designers could imagine, and even some they did not. That means extensive testing on Earth, using simulated environments that mimic the conditions of the target world. Mars rovers like Spirit and Opportunity already demonstrated a primitive form of this autonomy, making decisions about which rocks to examine and which paths to take without constant direction from mission control. The Precursor swarms will raise that capability to a level orders of magnitude higher. The philosophy behind this approach is called phased settlement, and it turns the arrival into a staged process rather than a single desperate gamble. The first phase is reconnaissance, using small, cheap probes to gather basic information. The second phase is preparation, using larger, more capable robots to build essential infrastructure. The third phase is production, where robots begin manufacturing fuel, oxygen, and building materials from local resources. Only after all three phases are complete does the fourth phase begin, the arrival of the crew. By then, the world is no longer a complete unknown. It is a site that has been tested, measured, and partially tamed by machines that worked tirelessly for years. The crew will step out of their ship into a world that already bears the marks of its new occupants: a landing pad, a shelter, a power grid, a cache of breathable air. All of it built by hands of metal and circuits, working in the dark, waiting patiently for the first human touch. That moment when a person finally stands on the surface and sees the work of these silent servants will be the culmination of a plan that began decades before. And it will mark the beginning of an even greater challenge, transforming that small robotic outpost into a home for generations. The crew steps off the ship into a world that has been prepared but is still hostile. The air outside the hull is unbreathable, the temperature may be far below freezing, and the radiation from the local star or from space itself could be lethal within minutes. Every breath they take, every step they make, must happen inside a sealed envelope that keeps the alien environment at bay. For the first settlers, that envelope will not be a city of glass and steel built over centuries. It will be a practical, rapidly deployable habitat constructed from materials they brought with them and from resources they extract from the ground. The most immediate solution is an inflatable module. These are not like party balloons. They are RE Chinese letter of high-strength fabrics, often made from materials like Vectran or Kevlar, that can be packed into a small volume for launch and then inflated with breathable air once on the surface. The Bigelow Aerospace Company has already tested expandable modules on the International Space Station, demonstrating that they can hold pressure, resist micrometeoroids, and provide a comfortable living space. On an alien world, a cluster of these inflatables connected by airtight tunnels forms the first settlement. They are lightweight, quick to set up, and can be shielded by piling local regolith on top of them to block radiation. But inflatables are only the first step. A more permanent solution lies underground. Many planetary bodies, including the Moon and Mars, show evidence of lava tubes, long caves formed by ancient volcanic flows. These tubes are natural shelters, already protected from radiation and micrometeoroids by meters of solid rock overhead. A crew can seal the entrances, pressurize the interior, and install lighting, heating, and life support systems. The rock itself provides thermal insulation, keeping the temperature stable against the brutal swings of day and night on the surface. Building inside a lava tube is like moving into a ready-made cave, needing only the addition of airtight walls and a supply of breathable air. For worlds with no natural caves, the settlers can dig their own. Robotic excavators, guided by the same autonomous systems that prepared the landing site, can carve chambers into the bedrock. The excavated rock is then processed into building materials, further reducing the need to import anything from Earth. These underground habitats can be expanded over time, creating a network of rooms, workshops, and farms that are safe from the surface environment. The domed city, a classic image of science fiction, is far more difficult to build on a first mission. A transparent dome that covers a large area must withstand enormous pressure differences if the interior is kept at Earth normal pressure while the outside is a vacuum or a thin atmosphere. The structural engineering required to hold back that force and to protect against impacts from debris makes a dome a project for a later generation, not for the first arrivals. For the initial settlement, the focus is on simplicity and redundancy. The habitat's walls are thick, its seals are multiple, and its airlocks are designed to fail safe. Every module has backup life support, and the entire network can be isolated if one section is breached. Sustainability is the central goal. The habitat is not a temporary camp. It must last for decades, supporting a growing population that will eventually have children and build a society. The water and air recycling systems, the food production, the power generation, all must be integrated into the habitat's design from the start. The structures themselves become part of the life support system, with algae tanks tucked into corridors, hydroponic gardens lining the walls, and waste processing units built into the floor. Every square meter of habitable space serves more than one purpose. This approach avoids the monumental effort of terraforming an entire planet, which would take centuries and require technologies far beyond anything available to the first settlers. Instead, the crew builds a tiny pocket of Earth inside a hostile world, a bubble that can grow as they learn to master the local environment. The bubble is the seed from which a true colony will sprout, but only if the habitat itself can sustain life indefinitely. That demands a closed-loop ecology where nothing is wasted and every molecule cycles back into use. The habitat becomes a living system, and the settlers become its caretakers. For the first time in human history, a civilization will be born inside a machine, not on an open plain. The success of that tiny world will determine whether the human journey to the stars ends in a single generation or continues for millennia. A ship moving at near light speed does not just cross space. It crosses time in a way that is impossible to predict without Einstein's equations. This is the breakthrough of time dilation and relativity management, a phenomenon that fundamentally changes the relationship between the crew and the world they left behind. At velocities approaching a significant fraction of the speed of light, time itself slows down for the travelers compared to the stationary observers on Earth. A journey that takes 50 years by Earth's calendar might feel like only 20 years inside the ship. The crew will age less than their contemporaries at home, and when they arrive at the destination star, they will be decades younger than the planet that launched them. For a crew that never plans to return, this effect is a pure advantage. The subjective travel time shrinks, meaning they experience fewer years of isolation, fewer birthdays spent in a metal tube, fewer decades of biological wear. A trip to a star system 40 light-years away, at a speed of 90% of light, would take about 44 years as measured on Earth, but only about 19 years inside the ship. That is the difference between a voyage that spans a career and one that spans a single decade of a person's life. But the same effect that shrinks the journey for the crew also destroys the possibility of meaningful communication with Earth. Even if the ship sends a laser message home, the signal travels at the speed of light, so it will take years to reach Earth, and the reply will take years to return. More subtly, because time is passing more slowly for the ship, the crew's clocks are ticking at a different rate than Earth's clocks. A simple query from the crew might arrive at Earth decades after it was sent, in terms of Earth's timeline, while the crew has only experienced a few months. Maintaining a coherent conversation over such a gap becomes impossible. The crew must accept that they are cut off not just by distance but by the very fabric of spacetime. This demands a new kind of navigation system, Ordinary GPS satellites already adjust for relativity because their orbital speed and altitude cause tiny time shifts that accumulate into meter-level errors. An interstellar ship moving at relativistic speeds must account for space-time curvature as it passes near massive stars or planets. Its clocks must be synchronized not with Earth but with a theoretical frame of reference that allows it to calculate its position and velocity with extreme precision. Any mistake in relativistic corrections could send the ship off course by millions of kilometers. The breakthrough here is not just better clocks, but an entirely new framework for navigation that treats time as a flexible dimension that shifts with speed and gravity. The crew will need a system that constantly measures their own time dilation relative to their star map and adjusts their trajectory accordingly. This is not a trivial software patch. It is a fundamental rethinking of how to travel through a universe where time does not tick uniformly. And when the journey ends, the crew faces a strange truth. Even if they could somehow turn around and return to Earth, centuries might have passed there while they aged only decades. The Earth they remember would be gone, replaced by a future that has no place for them. This is not merely a practical problem, it is an ethical question. When a crew leaves Earth for another star, they are not just departing a place. They are leaving a time, a moment in history that will never come again. Their families, their friends, their culture, all will continue without them. The crew becomes a living artifact of a bygone era, carrying the memories of a world that may have transformed into something unrecognizable. That realization must be faced before the journey begins. The crew must be prepared to say goodbye not just to a planet but to an entire timeline. And that goodbye raises a deeper question that no propulsion system can answer. What does it mean to leave home forever, knowing you can never go back? That decision to leave carries a weight no propulsion system can lighten. A crew that departs for another star is not just traveling through space. They are severing themselves from every legal system, every government, every protection that humanity has built over thousands of years. On Earth, a person accused of a crime has rights. A person in distress can call for help. A person who feels unsafe can move to another city. None of those guarantees exist on a ship adrift between the stars. The laws that apply on Earth end at the edge of the atmosphere. Beyond that, there is only silence and the rules that the crew bring with them. This is why an interstellar mission demands a breakthrough that has nothing to do with engines or materials. It demands a new kind of social contract, a framework of ethics and governance designed for a community that cannot call for help, cannot appeal to a higher court, and cannot escape from one another for decades or centuries. The first question is who holds authority. On a ship that must make life and death decisions instantly, there must be a clear chain of command, but that command must be legitimate in the eyes of everyone on board. It cannot be imposed by Earth after the ship has left, because Earth's voice will arrive years too late. The authority must be granted before launch, written into a charter that every crew member agrees to. That charter is not just a set of rules. It is a constitution, a founding document for a new society that will exist in isolation. It must define how leaders are chosen, how disputes are resolved, and what happens when someone breaks the rules. It must also protect basic human rights, even in the cramped and stressful environment of a starship. No one should be subjected to cruel treatment, and every individual must have a voice in decisions that affect their life. The most difficult question is informed consent. The first crew members, the ones who volunteer for the mission, can give their consent freely. They understand the risks because they have been trained and briefed for years. But what about the children born on the ship? They never chose to be born into that metal world. They never signed a waiver, and yet their lives will be shaped entirely by the mission, by the destination, by the decisions of their parents and the charter that was written before they existed. A just society must account for them. The charter must include a mechanism for future generations to have a say. perhaps through a council of elders that represents the interests of those who cannot yet speak for themselves. Some proposals even include a periodic referendum held every few years, where every adult on the ship votes on whether to continue the mission or to settle for a different world. That kind of democratic process is messy and slow, but it protects the fundamental principle that no person should be bound by a contract they never made. Catastrophic scenarios push these questions to the breaking point. What happens if the life support system begins to fail and there are only enough resources for half the crew to survive? Who decides who lives? Is it a lottery? Is it seniority? Is it the most medically fit? There is no perfect answer, but the Charter must provide a predetermined protocol, agreed upon in advance, so that the decision does not fall on a single overwhelmed captain in a moment of panic. The protocol must be transparent and fair. It must be the result of careful ethical reasoning, not a desperate choice made in the dark. It is the same kind of thinking that goes into triage protocols in emergency rooms, but with far higher stakes because no outside help will ever arrive. Existing space law offers very little guidance. The Outer Space Treaty, signed in 1967, is the foundation of international space law. It states that space shall be used for peaceful purposes, that no nation can claim sovereignty over a celestial body, and that astronauts are envoys of humanity. But the treaty was written for a time when the farthest humans traveled was the moon, a 3-day journey. It says nothing about a self-contained society that lives and dies in a metal can for a century. It does not address how to govern a population that grows and changes over generations, or how to enforce laws when the nearest court is light years away. The treaty is a beautiful starting point, but it is not enough. A mission to another star needs a new legal framework, a kind of interstellar constitution that lays out the rights and responsibilities of every person on board, from the moment of launch to the moment of arrival and beyond. This constitution must be recognized by Earth, but it must also be binding on the ship itself, even when Earth can no longer enforce it. It must include provisions for amending the Charter over time, because the needs of a society that exists for centuries will evolve. And it must include a mechanism for justice, a way to hold individuals accountable for harmful actions when there is no prison, no police, no court. Restorative justice, where the community works to repair the harm caused by a wrongdoing, may be more practical than punishment in such a confined environment. The crew must be trained not just in engineering and science, but in conflict resolution, in ethical reasoning, in the art of living together under impossible pressure. This is not a secondary concern. It is as foundational as the life support system. A society that cannot govern itself will tear itself apart long before the engines fail. And that leads directly to the final breakthrough, the one that ties all the others together, the creation of a generation ship that is not just a machine, but a civilization in miniature, designed from the beginning to carry humanity across the void and into a new future. A starship cannot launch on hope alone. Every breakthrough we have explored, from fusion engines to self-healing hulls, from artificial gravity to quantum communication, requires a river of money flowing without interruption for decades. No single nation on Earth today can afford the price tag alone. The combined cost of development, construction, and launch for a true interstellar mission would likely reach into the trillions of dollars, more than the entire global economy spends on space in a century. That kind of investment demands something far rarer than a new material or a better engine. It demands a unified political and economic will that spans generations, governments, and ideologies. The Apollo program of the 1960s is the closest example we have. At its peak, NASA consumed more than 4% of the entire United States federal budget, an astonishing commitment sustained for less than a decade. The goal was clear, the deadline was set, and the nation rallied behind a vision that seemed impossible. but Apollo was a sprint, not a marathon. An interstellar mission is a relay race that passes the baton from one generation to the next. The politicians who approved the first funding will be long gone before the ship even leaves the solar system. Their grandchildren's grandchildren may be alive when the first colonists step onto an alien world. Sustaining that level of commitment over a century or more has no precedent in human history. The challenge is not just money, but continuity. A change in government, a global recession, a war, or a shift in public priorities could halt the project halfway through. Every year of delay adds cost and risks losing the institutional knowledge built up by the previous generation of engineers. That is why the mission must be structured as a long-term investment, not a political spectacle. It may require an international consortium, something like a space agency for the whole world, funded by a dedicated tax or by an endowment that generates interest over decades. Private companies could contribute in exchange for future rights to resources or intellectual property. Universities and research institutes would provide the science. The key is to create a structure that survives the ups and downs of electoral cycles. Public support is equally fragile. The average person on Earth may struggle to see the point of spending trillions on a star mission when there are problems to solve at home. The rationale must be clear and compelling. It is not about escaping a broken planet, but about expanding the horizon of what humanity can achieve. The technologies developed for interstellar travel will spin off into medical imaging, energy production, material science, and computing, benefiting everyone on Earth. The mission itself becomes a symbol of human unity, a project that requires cooperation across borders and ideologies. In a world often divided by conflict, a shared goal among the stars could inspire a sense of common purpose that transcends politics. The economic argument also grows stronger over time. Space-based solar power, asteroid mining, and advanced manufacturing could generate enormous returns, turning the initial investment into a self-funding enterprise. The first missions might be robotic, proving the technology and generating revenue long before any human crew departs. The political will, once established, must be codified into treaties and agreements that lock in commitments for multiple decades. This is not a typical government project. It is a civilization-scale endeavor, and it demands a civilization-scale response. The hardest step is the first one. A single nation or a small coalition must decide that reaching another star is worth the cost. They must set aside short-term politics and embrace a vision that will outlive them. History shows that such moments of collective will are rare, but they happen. The pyramids, the great cathedrals, the Apollo program itself, all were built by people who knew they would never see the finished work. They built for those who would come after. That same spirit, scaled to the distance between stars, is the final breakthrough. Without it, all the technology in the world remains a beautiful dream. With it, the journey begins. 30 breakthroughs, each one a door that must be unlocked before a single human can stand beneath an alien sun. Some of these doors, like advanced solar sails or closed-loop life support, may swing open within the next 100 years. Others, like faster-than-light communication or antimatter engines that can be stored safely, may wait centuries for a revolution in physics that we cannot foresee today. And a few, like the political will to fund a generations-long mission, depend on something far more unpredictable than any equation. They depend on us. What this list makes clear is that reaching another star is not one problem but a cascade of problems, each one feeding into the next. You cannot solve propulsion without also solving radiation shielding. You cannot solve radiation shielding without self-healing materials. You cannot keep a crew healthy without artificial gravity and a robust social contract. The breakthroughs are not separate. They are a web, and the entire web must hold for the journey to succeed. But the very difficulty of the task reveals something about the people who would attempt it. No species builds a vessel for a voyage that will outlive its own builders unless that species believes in something beyond itself. The pyramids were built by people who would never see the top. The great cathedrals took centuries to complete, their architects knowing only the foundation, never the spire. An interstellar mission is the same kind of act, a declaration that the future matters more than the present. Every small step we take today, whether it is a better battery, a stronger composite, or a more just legal framework for space, brings that future closer. The breakthrough you work on, even if it is just learning to grow lettuce in a hydroponic chamber, is a thread in the same tapestry. None of the 30 breakthroughs is trivial. None can be skipped. Which one do you think will happen first? The fusion engine that cuts travel time from centuries to decades. The artificial intelligence that can run a ship without human oversight. Or perhaps something simpler, like the genetic tweak that lets us hibernate through the long years. I would love to hear your thoughts in the comments. Subscribe if you want to follow the journey from dream to blueprint, and from blueprint to the day the first starship finally departs. The road is long, but we have already taken the first step just by asking the question.